Good morning, everyone. Today we'll be presenting our senior design project, which consists of a solar heat power air conditioning for the FIU trolley. Our team members are Adrian, Gonzalez, Daniel, Pico, and myself, Yetsey, Suero. In this project, we face the problem of replacing the electrically driven AC compressor of the with a solar heat power air conditioning for the FIU trolley. It's got to be environmentally friendly, as cost effective as possible, as well as efficient. Now, the reason we're using an external source of energy is so that we don't deplete the driving range of the trolleys, which we know is a typical problem of electrical vehicles today. So we're also using solar heat to power the chiller because it is a clean, renewable, and easy to harvest source of energy. Now, this is a multi-team project because the power for our system will be supplied by a solar collector provided by another team who's currently working on that. Now, the project objectives are pretty much to redesign and install these absorption chiller to operate in solar heat. We also have to analyze and determine the proper amount of heat for the trolley, as well as fabricate, redesign, and install the complete hot and water supply and return piping circuits. We also have to integrate the solar collector design with this other team with our cooling system so that it operates as efficient as possible. So we have to coordinate with this team so they provide the correct amount of power for our system. Finally, we want to improve our ability to apply physical principles to solve real-life problems. Now, the motivation for this project is pretty much to promote, the use of clean energy to solve real-life problems. We also want to show that existing technologies can still be applied in innovative ways, and of course, we want to solve the problem of adapting an absorption chiller to a small system as this trolley, since it usually is used for bigger systems like to power in buildings and industries. And finally, we want to provide cooling options to residents and visitors of Sweetwater. Now, these are some of the applicable standards that we found at the ASME B31A, which is related to gas transportation and distribution. This will be we are designing the piping circuit for hot and chilled water. And these are some additional standards which can apply to the Florida Department of Transportation. Regulate the mass transit, so we might need one, and we also might need the EPA for which has to do with the type of refrigerant used, and finally the ESO to ensure global standardization and research.
My name is Adrian Gonzalez. I'm here to talk about the design. Our design starts with a gas-fired absorption chiller manufactured by Rober Industries. There's an example of the chiller that we're using as our basis. We're going to have a custom designed hot water system, heat exchanger to replace the gas-fired burner that comes with the Rober. We're going to use high voltage, low amperage motors, both for the chill water, hot water, and as well as the fan coil blower, so that those will be powered by the battery, but again, high voltage, low amperage, so there will be very little draw on the battery. And alternate design number one is to use lithium bromide instead of the ammonia that comes inside the Rober chiller. Unfortunately, due to cost constraints, converting the system would be very expensive at this point for our prototype, but that is definitely something that should be researched in future iterations. Alternate design number two is to combine the solar collector with a natural gas burner. The idea being that in scenarios where the amount of solar heat available, whether it be a cloudy day or the temperature is not that high, we can have a booster. So we would install an inline burner on the hot water coming in, so that if it doesn't reach the necessary temperature that required for our reaction, which in our case is 305 degrees, we can boost just a little bit more using a replaceable natural gas tank to be installed on the trolley. It would allow for a short-term proof of concept. So that is a very good option for us right now. Alternate design number 3 is to include on the battery-powered trolley, to design some kind of a heat exchange interface between the drive motor and batteries, which tend to be a problem overheating. So design some kind of heat exchange with that system to recover that heat as well. Unfortunately, that system, the drive system is not designed yet for the trolley, so it's impossible for us to integrate that at this point. And then alternate design number 4, which is, in this case, this is our ideal design. It combines the solar collector with a natural gas burner and thermal engine heat. If the trolley is to go plug-in hybrid, the existing combustion engine could be converted to run on natural gas, replace the fuel tank with a compressed natural gas tank, and that would give us the extended driving range on the trolley. So it would run a generator that would power the batteries. We could access the natural gas tank to feed our booster in case we don't have enough heat. Plus, we can design a heat exchange for the internal combustion engine, whether it be through the exhaust or other means of capturing. So we would capture the heat from the engine, we would capture the solar, and in the last case, if we still needed some more heat, we could always use the burner as a third step. Our global impact is, again, to reduce significantly the harmful emissions from mass transit. Our design can be incorporated, whether it's just on the trolley, buses, trains, any mass transit application that's going to be exposed to the sun. To utilize renewable energy sources that are abundantly available. Solar, natural gas are easily accessible. Avoid the use of expensive rare earth minerals. Right now, there's a big push, obviously, the lithium batteries, whatever. There's expensive earth metals that are being proliferated in seeking energy efficiency, but they're very expensive, so they're limited in their reach. In our case, we're using stuff that is available worldwide, and so that allows us to expand our reach.
I'm going to go ahead and talk a little bit about the budget for this project. As you see here, we have the absorption chiller. We physically already have the chiller. That was procured through a grant from a local company. Was it, well, anyways, the cost was $6,500. We're projecting for the water pumps and the other amenities required in order to actually chill the interior of the trolley and to do the additional system and to also connect that a solar collector and have that take the place of the burner. That is going to require some piping and there's also some pumping. So altogether, we're looking at about $13,500 just for the procurement of supplies. Just as a rough estimate, 160 work hours should be used to complete this project. 5 hours per week for 32 weeks. It's not a very time-intensive project, but breaking it apart into 5-hour segments is feasible because you're going to be overworking whoever's doing this project, mainly us. The salary is projecting just an average salary for a salaried engineer, broken down to an hourly rate. The total estimated labor cost is an additional $6,600 and change for a total cost, projected cost, of $20,109. Our current progress, the grant was received from ASHRAE, the Miami chapter of the American Society for Heating and Refrigeration, etc. The grant money was brought in through the courtesy of AMP Air Conditioning, and Rober is the brand of the absorption chiller that was purchased. This right here is a simple model. I know it's very difficult to see from there, but it's basically just a model of the rearward space of the trolley, and that is the idea that we're looking to retrofit. In an earlier picture, and I'm sure you've seen how your air conditioning unit on the outside of your house looks. There's a huge condenser coil, and then there's a section where there's electronics. In the case of the absorber or the absorption chiller, all of the segments for the absorber are inside of that housing as well as the electronics, and then it's just the massive coil. We're limiting the massive coil, and those components will be broken down and either laid horizontally according to the orientation at present or standing vertically in that rearward space of the trolley. This is the timeline. Presently, we already have our conceptual design more or less figured out. We still have to draw plans for it, and at that point we will be doing our analysis and optimization, so that puts us on par with our time constraints. By the end of the summer, we're looking at having our manufacturing at least midway, if not completely done, so that by September, November, we're looking at testing and proving that the concept works. First outside of the trolley, and then trying to install it to the back. Thank you, ladies and gentlemen, for your time.
Thank you. Questions for the team? Comments?
Sir?
Yes, sir.
So, because you haven't gone all the way to analysis portion of this, one thing that comes into mind is it is a movable platform, right? You have your trolley, and you're talking about the heat exchange portion of it being using a flame, some sort of a heat exchange using propane or LP,
Yes.
using a flame, right? Any considerations, aside from the DOT portion, which is this system has to be safe in order to operate on the roads, but for the sake of the safety and the functionality of having this plume be exactly where it should be to provide the best efficiency at that level. I worry that is there any brainstorm at this level of, is it going to be multiple plumes? Is it going to be some sort of like a barbecue type, rotisserie type of things of that nature? Is what's kind of moving, because if this truck is moving left and right, you're taking turns, you're accelerating, you're braking, this plume is going to be fluctuating all over the place. So
Absolutely. To answer your question, the way that our system designed is on the roof of the trolley is the solar collector. So the water pipe coming back from the solar collector will be a vertical pipe. The way that the existing chiller design, the gas-fired chiller, it is an enclosed burner around the generator. All right, so it is a direct heat in an enclosed capacity. So because we're going to be designing our system in the back portion of the trolley where there are no passengers, we're looking at either encasing it inside with proper ventilation inside a fireproof barrier, whether we use some kind of fire barrier, whether it's 3M or any other case to protect it, or possibly putting the burner on outside. But again, it would be enclosed, and the pipe would be protected, the exhaust pipe. So because we do need combustion air and as well as exhaust for that. So that is a design consideration that we are taking into account. But we definitely are installing in the back part of the trolley where there are no passengers, and so that is
So far, that's our consideration.
right.
Just to add a couple points to that as well, though. The first thing that has to happen for us is, first we need to determine the size of an interfacing coil. That's why there has been very little analysis so far. First we have to tear down that machine. There's only a certain portion of what is referred to as the generator in an absorption chilling unit, and that is actually where the burners are lined up around the pressure vessel where the ammonium water solution is pumped into it. So it's completely sealed off, but it's direct heat. It's fire hitting the outside of the vessel. So our idea is to remove that from around the generator, and we're going to determine the proper dimensions for a coil where that is going to receive that hot water from the solar collector and then circulate it. The burner, of course, will be put in line, but like he said, everything is in the back of the trolley. That space that we showed you earlier, I wish we could blow it up, but it's actually a rather large space, approximately 65 inches in width and about 70 or 72 inches in height at the back end of the trolley. And the actual length and depth of it is close to 100 inches. So it's plenty of space away from where there's going to be passengers. As far as ventilation is concerned, the trick would be how we lay out those individual components. There's some parts we want hot and some parts we want to keep cool. So whichever ones are the ones that are most dangerous, hence the natural gas, that's going to be burning. That should have an exhaust vent, and that's also why we're aiming at putting it near the back wall of the trolley. Because right there, it's a lot easier to modify and have proper ventilation.
Now, what you're not seeing in this picture is actually, this hump here is the rear axle. The trolley is from here forward.
Yeah.
So
This
we've
is
isolated
back.
the portion that is unused and away from the passengers, and this is where all of our design is going to be happening.
Any other questions?
I guess two question areas. One is vibration. Are you planning to do any vibration analysis?
There will have to be vibration analysis. For one, the trolley itself, of course, is going to have its own suspension, but all of these parts are not just going to be, anchored to the wood. This is a wooden trolley. It's very old. At any rate, it's unreliable for supporting most of these weights. So some sort of a cage, and even including shock mounting of a cage, is a very reasonable approach to take to it. However, we're not at that phase yet. We're more concerned with trying to figure out that coil size and how we lay out the components. Once that's done, there will be a frame. And, there will be
And why I ask it is also how you transfer the gas. Those hoses need to have some level of flexibility to ensure that you don't have a vibration fracture. You've got an exhaust pipe coming out the back end of the trolley, and you've got a natural gas source. You have a nice fire.
Yeah.
So,
Absolutely, but to further this, the vibrations, because it is an absorption chiller, we don't have the same vibrating compressor, so our components do not produce the same vibrations as a standard air
Yeah,
conditioner.
by themselves.
that's only half the problem.
Right, that's only half, but again, but we did eliminate, we eliminated half the problem. Just for reference, I am an air conditioning contractor, so we typically have to deal with the internal vibration. And so we have the rubber mounts and spring mounts for our system. So half of the equation is already answered. Our system doesn't vibrate by itself. So we have to deal with keeping our system steady with the movement of the trolley.
Yeah, that's why we feel separating it in its own frame and having that shock mounted to the chassis of the trolley, that's the best approach. Because within those components, like you were saying, there's no vibration, or little or no vibration. So they're mounted separate, and that way you keep everybody nice and isolated, vibration and thermal and stuff.
Any questions?
Hey, okay, don't leave, please. We're all done actually, but